Awesome. All right. Welcome, everyone. Thank you so much for coming. This is the part two of our project Phobos, and you had a glimpse of it last week, but we'll be going into much more details about rockets, tree, and the components of the rocket itself. So, yeah, like Cass said before, if you guys have any questions at all, like feel free to either put on the chat or unmute yourselves. And ask the questions because, always happy to like answer anything along the way. All right.
Cool. So first of all, there's an update to the workshops. We've changed the timetable a little bit. We've mixed it up a bit, but I think it's for the better because we're going to be hopefully getting some of you to design and print your own rockets. It's going to be a bit more practical. And in order to do that, we've added 2 workshops immediately after this one. So in the next 2 weeks, there's going to be open rocket workshops, which are workshops related to some simulation software for rockets and designing rockets, which you'll see very soon. And as a result, we've pushed back some of the other workshops, but we'll get to those in due time. But I think, yeah, this is a much more exciting list of workshops that we've got lined up for you this sem. And as Anne mentioned, we've got a new home for the workshops on GitHub, where we're going to have all the information related to these workshops. So you're going to be able to access all the PDF slides and any recordings that we do, anything like that. It's all going to be sent to the GitHub. So in the future, we won't be uploading the slides to Slack. We'll just we'll send you all straight to the GitHub. And in terms of week 2 revision, I think just very briefly, we will cover the 4 sort of subsystems on the rocket. So for those of you who were here last week, we've got the 4 subsystems. We've got aerodynamics, in other words, external structures, which is essentially the airframe of the rocket. And we have internal structures, which is anything inside mechanically. And we have the avionics and payload, so all the electronics and any electronics going inside the payload as well. And also on the software side, we have the simulations team. And this is the open rocket software that we mentioned earlier. So that's a quick revision for week 2, but we've got so much stuff to go through. I think it'd be best to just jump straight into it, right, Anne?
Yeah, awesome.
That's a list of terms that we mention in these slides. So if you're comfortable with everything on this slide, then you're definitely ready to work with Project Phobos.
Did we want to skip to like where we were up to last time?
Yeah, sure.
Awesome.
So last week we went through these first few slides, just describing basics of propulsion. We wanted to mention that this slide refers to liquid fuel, but we're using solid fuel. So the oxidizer and the fuel are mixed in one continuous solid for our motor. So Anne, would you like to jump us into this one?
Yeah, so this is just kind of like an overview of the different components of a rocket. At the tip, obviously, you've got your nose cone, and we're going to go through each section in greater detail. So the first part of the nose cone, the whole point of a nose cone is to modulate the incoming air. It helps minimize the drag, just because of its more gradual transition. And it helps define that main characteristic when it comes to the aerodynamic of the rocket. The nose cone design can vary, and it depends on the situation, and in particular, the speed that the rocket will be traveling at. So for a low velocity, maybe subsonic airflow, you would kind of want more of a rounded type of nose cone. The particular reason is that will help minimize the drag for the rocket. But for higher powered rocket that might experience supersonic flows, so at much higher velocity flows where the flow is at a higher than the speed of sound, you would kind of want more pointed type of nose cone. And the reason for that is because at supersonic speed, you're dealing with flow shock, which you might learn in fluid dynamics, or maybe later on when you've reached there. But to essentially, pointed nose cones will help reduce the drag during those high speed velocities. Here on the side, you can see that there are 3 types that we've kind of listed of like different shapes of nose cones. One is the ellipse, that's kind of like your parabolic, more rounded shape, so good for subsonic flows. And then you've got your tangent OGV. I think I pronounced that right. I'm not sure. Ogive, okay. So that one is kind of made up of a section of a circle, and it can be rounded at the tip, or the radius varies at the tip. And then you've got your hack, and from what I understand about the hack shape is that this isn't based off of sections of shapes. This is based off of a formula made by some man named Hack.
Yeah.
And it's based off of that formula of trying to minimize drag as much as possible.
Mm-hmm. Yeah, so next up we've got the ballast, which is typically right up inside the nose cone. And it's essentially just some weight that you add to the rocket to adjust how high it goes. In other words, you can adjust and tune the apogee, which is the peak altitude. Depending on different weather conditions, the rocket will go to different apogees. So what we do is we have a weather balloon that takes the weather data on the day of the launch, and we pump the weather data into the simulation, which will estimate the ballast that we need, i.e. how much mass do we need to put up here to reach as close as possible to 10,000 feet apogee at the peak of our flight. So we've got this educational film that explains how ballast might be used. This bloke has chosen to use an anvil as his ballast, and the ballast keeps him at a consistent altitude. So that's his current apogee using that mass of whatever the anvil weighs. He then ejects the ballast, which adjusts the equilibrium altitude and deploys the main parachute, which sends him into a ballistic descent.
Hopefully our rocket doesn't do that.
Hopefully not. This isn't the design feature of our rocket, but then he descends because he deployed his rocket, he lands successfully, and the ballast is there to protect him from getting run over. So yeah, ballasts are very useful. And now I'll go back to sharing the PDF. All right, cool. Can you see the reaction wheel slide?
Yep, we can.
Awesome. All right.
All right. So this is kind of like brushing over a reaction wheel and what it does, but basically it's a type of flywheel, and usually used in parallel with gimbals or sensors to kind of get like sensors that would detect its orientation. But basically what it does is it is used for attitude stability. So attitude means the orientation of the rocket. For these types, you can have a combination of, in this photo, there's 4 of them, but basically they're just flywheels where they would spin, and that would create angular momentum and would kind of rotate the rocket along the 3 different axes that it would have. In our rocket design, I believe we only have 1 reaction wheel for 1 degree of freedom, and that's meant to help orientate its roll. So there are 3 types of rotations that a rocket would experience from its 3 axes, so X, Y, and Z, and that's roll, pitch, and yaw. This particular one that we are thinking of using will be for roll stability, and that's to help with the camera, I think.
Yeah, just to help with our footage. Mm-hmm. Oh yeah, there's a bit more info on these as well.
Oh, yeah. So in this one, like I said, it is usually used in parallel with some sort of sensor or something to give indication of its current orientation. And in this case, we're going to use the inertial measurement unit. I think that's like a combination of gyroscopes and certain actuators. So that would give you indication of not only its orientation, but also probably other information as well that are useful for us. It will use a PID control system. So in terms of what that means, there are different types of controllers that this can be used in parallel with. PID is kind of like a feedback control system to constantly give feedback on what its orientation is, and that that reaction wheel will be used as kind of like an actuator to like try and steer it back into the position that you want it to be at. So yeah, a really useful kind of tool.
Yep. And next we have the payload. We spoke a bit about the payload last week. Essentially, the main goal of this payload at the moment is to keep track of the trajectory of the rocket without using GPS. And it's actually a capstone project for the Ares team. And it's all kept inside what's called a CubeSat, which is a standard form factor for miniaturized satellite, 10 by 10 centimeters. And it's going to be transmitting data in real time, and that's going to be constantly sent back and forth from the ground to the rocket. So that's called telemetry. And we're going to have an onboard camera, which Anne mentioned as well. And as I said, it's going to be a capstone without using GPS. So GPS is a very reliable way of tracking the trajectory of the rocket. But the challenge for us is to try and find another method, such as barometers for finding the altitude, or IMUs for measuring the acceleration and rotation of the rocket. So that's some of the components that might be inside.
Awesome. So now we're at the section where you would deploy a drogue chute. So a drogue chute is a smaller parachute, and it's ideally going to be ejected at apogee. So once it reaches the highest point, we're going to eject the drogue chute, and its main kind of function is to try and slow down the rocket and stabilize its descent to a sufficient speed so that when the main parachute is deployed, it's a success. It will successfully be able to slow down the rocket sufficiently. Yeah. So in this case, we're aiming to have that drogue chute a reduced velocity to almost 30 meters per second. Yeah.
Mm-hmm. And in order to deploy the parachute in the first place, we have an ejection system, which is built into this sort of cavity here between these two bulkheads. And there are a few different designs that we have at the moment floating around. One option is to have a little servo motor here that drives a pin into this canister. Another option is to have a spring-loaded design. And the common design point here is that they all pierce this canister, which releases high pressure carbon dioxide gas into this area here. And that will build up pressure and apply forces to these bulkheads, which are these white discs on either side. And when that pressure is applied, it will snap some shear pins, which are attached to the black airframe, shown here in black. And that will snap these shear pins and allow the rocket to split into two, which you can see in this picture in the center here. So the parachute can come out and we're not losing any parts of the airframe. And we actually have two of these. We have one for the Drogue chute and one for the main parachute back here that we're going to have a look at as well.
Awesome. All right, in terms of avionics, like mentioned, it will be a series of sensors to help track the rocket during its flight. That's kind of one of the base requirements in terms of what the ARUC has given us. It will also have a series of altimeters and transducers and radios for that telecommunication and tracking. It would also have that IMUS, which was that unit that we mentioned to give us indication of its velocity, its orientation during flight as well. Is there anything else you think that needs to be added as well for this section, Cass?
No, I think, I think it's just worth mentioning that this is the fundamental electronics, and there's the difference between the avionics bay and the payload bay is that all of the fundamental essential electronics for the rocket will be in the avionics bay, and we'll have our true GPS signal inside this avionics bay. And the payload is more for auxiliary electronics for that extra challenge that we're trying to attempt. And
it is also worth kind of mentioning that that avionics bay is in between two bulkheads with I think 2 rods, is it, that kind of like holds the bay together.
Yep.
So yeah.
Cool. Then we have the main parachute, and it works in a very similar fashion to the Drogue parachute that we mentioned, except it's fired after the Drogue parachute. So the Drogue parachute gets us to a decent descent speed. And once we've slowed right down, then we can apply the main chute to get us at a safe landing speed. And it's really very similar to the Drogue chute. You just shoot the Drogue chute first.
Okay, so the airframe is highly important because number one, it has to withstand the stresses of the thrust from the rocket motor, and it's also going to have to withstand the compression from the airflow coming, hitting against the rocket as it's going through flight. For low-powered rocket, it's usually made from like, plastic or cardboard or wood or some sort of weaker material. But when we're dealing with high-powered rocket, we're dealing with a lot of thrust. So that means that that's a lot of stress that it would have to be able to withstand. And so we need better materials for that. In terms of what we've decided to use, we're using carbon fiber. To kind of explain what carbon fiber is, well, it's just basically small fibers made up of carbon, and they're woven into kind of like a fabric material. And usually it would be made with other materials to form a composite. So in this case, we use like a plastic epoxy resin to lay it on top and kind of like create a like a sandwich, I guess. That's one method to kind of create a composite of the carbon fiber, is to lay the fabric of the carbon fiber and then lay the epoxy resin on top, and then you keep doing that, kind of like paper mache, I guess, and you do it on top of a mold, and that can help form the airframe. The other method, I think, is that we've been looking at exploring is the infusion process. From what I understand, you would lay the fiber in the mold and you'd put like a plastic bag and you'd vacuum seal it. And then you'd kind of feed the resin through and have it infused in with the layers of carbon fiber. And that dries out, and then you end up with your kind of very hard and strong carbon fiber. Of course, it's quite brittle as well, but because this kind of, we're more interested in the fact that it has to be strong against compression, and it's not too bad that it's brittle.
Yep.
Does
I
that
think
video work?
would be a good time to show this video. Yeah,
Yeah,
I'll blitz
cool.
through it because it's like 20 minutes long, but the idea is it just shows a bit of info on how carbon fiber layup works. So layup is the process of, I suppose, manufacturing from the actual fabric that Anne was mentioning, plus the epoxy resin. And this bloke's making drone propellers using carbon fiber. So what he does is he's got the fabric sheets there, the carbon fiber sheets, and he's going to mix this epoxy resin. Hopefully you can see it there in that cup. So that's the sort of glue that holds the different layers of carbon fibers together. And it's the composite of those two materials that makes carbon fiber polymer so strong. And what you do is you spread this, let's see if we can find it. Yeah, you spread a layer of this sort of epoxy glue down, and then put a layer of carbon fiber down and push out all the bubbles using this special tool. And you do several layers like that. You put more epoxy on, more fiber on. I think you apply the fibers in different directions so that you can have strength in multiple directions, so it doesn't just snap in one direction. And this is the sort of mold that he wants to apply the carbon fiber to, because it's still flexible before the resin has dried. And what he does here is he's going to place the foam mold on this silver plate here and then wrap the carbon fiber around, which you can see here. And that's going to stick nice and tight to that mold, and it's going to dry the epoxy. You put it up to an elevated temperature. I can't remember exactly how hot it is. Might be something like 50 degrees for 5 hours. And that will solidify all the material. You want it nice and tight over that mold. And that's just an example of how you can make something out of carbon fiber. That's going to make a really light, really strong, and really stiff material. And I think the weight component is really important for our particular application. I think that's the main benefit of carbon fiber over something like fiberglass. Yeah. So we'll move on to something that's slightly less exciting than creating carbon fiber, and that is the centering rings. And it's essentially just some polymer, i.e. plastic, tough plastic, that you wrap around the motor, and it just keeps everything centered and in place, because if the motor's rattling around inside the airframe, then the trajectory is going to be really unpredictable. So it just is one of the interior structures that we need to keep everything structurally sound. It's pretty basic.
All right, so the bulkhead is kind of like that component that's kind of sandwiched where the motor area is, and it helps transfer the motor thrust throughout to the entire frame of the rocket. It's there at the avionics side as well to help protect the avionics bay from the ejection charges when the parachutes are deployed. The eye nut is attached at the end here. Oh, my mouse, you can't see my mouse.
I'll circle it. Yeah. Hopefully you can see my cursor.
Yeah, so that eye nut attachment is where the parachute shock cord will be threaded in through. And so when the parachute obviously deploys, that shock cord will pull that eye nut, and that eye nut will try and distribute that shock throughout the bulkhead. So yeah, there are many uses for the bulkhead. The main ones are for the motor and for the parachute and avionics bay areas.
Mm-hmm. And I'll just mention quickly that we're using polycarbonate for these thin bulkheads that you can see at the forward end. And we're using what's called XPS, which is extruded polystyrene. It's basically really tough foam. and we're coating that in fiberglass, and that will go over here for the motor bulkhead. And that's actually this image here. So we need a lot more thermal resistance and I suppose resistance to the motor thrust for that bulkhead. So it's a bit chonkier than the other ones. And did you want to do this slide as well, or you want me to do it?
Yeah, okay, I can do this one. So basically, when we're dealing with rockets, there are 3 different types of rocket motors that you could choose from. Obviously, we've been constrained with the one type, which is solid. So a solid one is just a solid fuel with an oxidizer that is mixed together. The liquid rocket motor are when you've got both liquid fuel and liquid oxidizers. They're stored separately, as you can see in that image. Obviously, these are way more like that's like 95% of it is just the rocket motor, but in that case, you can see that they're separate and they'd come together in the chamber, and where they will mix and create thrust. So yeah, in terms of high-powered rocket, which is what we're interested in, we deal with a range of rocket motors, and these rocket motors are categorized by impulse. So, oh, I think
That's
I
this slide.
changed. Oh, okay. Yeah. So with impulse, you have it categorized by letters. So A is categorized as like the smallest impulse that a rocket motor could have. And in high-powered rocket, we deal with the range of H or larger than H. And the certifications are basically categorized in terms of those impulse categories. So for an L1 certificate, we're dealing with an impulse of around 160 to 640 Newton second. And L2 is a higher thrust, and so that's high impulse, and it'd be around the 640 to 5,000 Newton second. Yeah, that's kind of all I wanted to cover in terms of motors. Is there anything else you'd want to mention, Cass?
No, I think that's all good.
Cool.
Can move on to flight stability. So this is a really important concept. So you'll see with a lot of amateur rocketry, they might design and build a rocket and they haven't really thought about these concepts that we're going to explain. It looks really cool. It looks like a rocket, but then when they launch it, it just spirals out of control and it's just absolute chaos, a disaster. But what's the difference between a rocket like that and a professionally designed rocket that will go directly in a straight line? And the main difference, I would say, is the flight stability, i.e. the center of pressure versus the center of gravity. So these are 2 really important concepts to keep your rocket flying in a straight line and not just crashing into the ground. So the first concept is center of pressure, which is the point upon the rocket upon which the sum of all aerodynamic forces could be seen as. So it's very similar to the center of gravity, which you're probably familiar with from your physics classes, except it's the center of the pressure forces, and it's this equation here. So it's the integral of the distance to that particular point on the rocket multiplied by the pressure force on that point on the rocket, and you integrate over the entire body of the rocket in 3D, and then you divide it by the total pressure force, and that will give you, very similar to the center of gravity, it will give you the center of pressure, where if you had to combine all of the pressure forces into a single point, this is the point at which it would act. And then another very similar concept that you're all probably familiar with is the center of gravity. It's just the centroid of the distributed mass, which is the point upon which you could balance it if you were balancing it on the tip of a pencil. And it's also the point at which you can apply a force to the rocket without the rocket rotating. You can just push on the rocket at this point and the whole rocket moves without spiraling. So these 2 are really closely related. We need the center of pressure to be behind the center of gravity. Okay, so if this rocket starts to twist out of line, if it's not going in a straight line, it starts to twist away, the pressure forces from the air will be applied at this red point, the center of pressure. But the rocket will rotate about the center of gravity here. This is the point about which the rocket rotates. So if you think about it, if the pressure forces are applied behind the center of gravity, then that's going to bring the rocket back into alignment. Whereas if the pressure force was applied in front of the center of gravity, then that's just going to make that slight misalignment even worse, which is going to cause the rocket to spiral out of control. So a general rule of thumb is that the center of pressure should be 1 to 2 calibers aft of the center of gravity. In English, that means should be 1 to 2 diameters behind the center of gravity, okay? And that's really important for stabilizing the rocket.
Awesome. Yeah, so fins kind of are highly important because number one, like what Cas mentioned, they move the center of pressure rearwards. So that's crucial for stability because we kind of want that center of pressure to be more towards that rear section of the rocket. And as you can see in flight, usually you'd have air flowing from that leading edge of a fin to the trailing edge of the fin. So basically what happens is if a rocket was to turn, the fins opposite to the turn will move the airflow, and in a way it's kind of that same concept of restoring it back to its original position. This is known as kind of like restoration. Because they are relatively thin structures, you'd have to be conscious about its two main modes of failure. Number one could be aerodynamic flutter. If you've done if you've done vibrations before, you might be familiar with that term, but basically it's like a dynamic instability where it would reach a point of just uncontrolled self-oscillation. And the second thing that's important to consider is the method of how it's attached, because, you know, the way that we attach it to the rocket, if it was to fall out during flight due to the high forces of airflow, then, you know, you're in a little bit of a trouble. But yeah, ideally we'd want a minimum of around 3 fins. That's kind of like convention wise. I feel like 2 would be very useless, but 3 kind of provides you with that minimum stability.
I don't remember the French type.
Just mute that person. Sorry. I just wanted to show a quick picture on the topic of fins. Oh, actually, I can just keep sharing the PDF. From these slides, from last week's slides, this picture here shows how much flutter can occur in those fins. They're getting seriously bent. So that's kind of what we have to design against. That's what we're up against. We're up against some serious deflection there, and there's a lot of stress there. So that could be something that you could design with us. All right. Did you want to talk about this one? Because I think you made this slide, Anne.
Oh, I removed it when I was like fixing up the slides, but it must have not updated. I guess kind of like in concept, mass is important because it can help determine like the rocket's end performance. You'd notice that when we're designing rockets, a lot of the time, the major mass actually comes from the propulsion side. So it comes from the rocket engine or the rocket motor. And so in commercial rockets, you can find that like the mass factor can go up to like almost 0.8, which means that it's around roughly 80% of the rocket's mass. But in rocket models, we're not dealing with gigantic amount of thrust needing to like take us off out of orbit. So we would deal with mainly around as low as 0.15. So that's around 15% of the rocket's mass. But yeah, it's an important thing to kind of consider because mass means everything to us. We want ours to be lightweight and all of that, but we also want there to be enough thrust. And so obviously we need a sufficient amount of fuel and rocket motor for that.
And I think our mass is pretty close to the maximum that's allowed. I think 13 kilos off the top of my head is the maximum that we're allowed for the competition, and we're like pushing that. So yeah, mass is definitely a limiting factor for us. Okay, so we won't dwell on this too long, but it's really important that we at least mention it to you all. You have to be really thorough and systematic about safety on these kinds of projects. So if you're working with us, there are a couple of techniques that you'll be using to check that everything is safe so that we don't have a catastrophic disaster on launch day that could, well, get us bad results in the competition or even worse, injure someone. So failure modes and effects analysis is where you think about each little component of the rocket and possible failure modes for that. And we consider how likely they are and what the consequences are and how detectable it is. So what we do is we allocate a value from 0 to 10 to each of those, how likely it is, how serious the consequences would be, and how likely it is to go undetected. And that gives us this value called RPN, which is a risk number, essentially. It tells us how risky is it. And the higher the risk number, the more we need to do to avoid that staying high. So we need to make sure that we've implemented some sort of safety measure to make sure that we don't have any high risk factors. Here we go. Severity times occurrence times detectability equals risk priority number. So the higher that RPN is, the more attention we need to pay because it's more likely that something's going to go wrong. And if it does go wrong, it might hurt someone. And there's also this method called the risk register where it's similar. You take the likelihood and the consequence and you make a table, and anything that falls into this red to yellow area that is likely to happen or would have severe consequences, we need to implement some sort of safety measures to make sure we get it back down to this green area, which means it's not going to have severe consequences and it's also not very likely to happen. So the proposed solutions is what we're looking for when we do all this safety stuff. And it's a very similar calculation. I won't go into it right now. Anyway, Anne?
Awesome. Yeah, so this is something that we're going to be working with in future workshops, but CADing will be kind of like our friend. CAD is just a three-dimensional modeling software that we use to help model the designs that we have. And from that, we can apply analysis into it, such as finite element analysis or computational fluid dynamics to kind of get an understanding of how the rocket would perform without needing to, build it and then test it. So it's a really cost-effective way of doing things. In our case, we're going to be using Onshape, which is a cloud-based, on-the-web kind of thing. So you don't have to download anything because it works on your web browser and it's a really effective tool. It also has a lot of learning modules that is, out there for you guys as well. So we will be doing 2 workshops in the future, learning how to use Onshape, and we'll be trying to build our own rocket as well. So yeah, going to be exciting things.
Yeah, cool. And once we've completed the 3D model using the CAD software, we can apply, as Anne said, we can apply some sort of testing without having to destroy the physical thing. So FEA is finite element analysis. A lot of engineering students would have heard of this term before. you basically break your 3D model into lots of tiny little pieces and apply basic stress strain, sort of basic physical principles to each of those little pieces, and those then interact with each other, and it gives us an approximation of how that large 3D body is going to react to different forces, what kind of stresses we're going to get, and what kind of displacements we're going to get. So this image that in the center here, the red areas are probably areas of higher stress if a force is being applied. But they could also be areas of larger displacement. And we're going to be performing a lot of this on our rocket model.
All right. So CFD, which obviously stands for computational fluid dynamics, is a way of analyzing the fluid around a body. So in this case, we're interested about the fluid flow around the rocket. It works kind of opposite to how FEA works in that we're interested in looking at the actual structure or the body, but instead computational fluid dynamics, we're interested about the space around that body. So instead what we do is we would mesh the space around the body, and we would then use, well, the computer would then do hard calculations, and it's called numerical methods or approximation because, as we would know in fluid dynamics, Navier-Stokes is a very difficult equation to solve. And it's one of those like unsolvable kind of thing or challenges that mathematicians are still trying to understand. And so instead, the computer will use approximation and numerical methods to help analyze the fluid flow. This gives us a good idea of the heat, the pressure, the fluid velocity, and the aerodynamics around the structure. So it's a really powerful tool because, you know, you wouldn't want to be using hand calculations to try and understand this. It can become a bit of a monster when you're dealing with very complex shapes.
Yeah, absolutely. And the software we're going to be using down the track, and we'll probably do workshops on this SEM 2 at this point. The software is ANSYS. It's a really powerful, I'd say industry standard software for not only the 3D modeling, but also the FEA and CFD. And we can do coupled FEA and CFD. So that's called multi-physics simulation. What that means is the fluids will interact with the body will then deform, and the deformation of the body will then alter the fluid in turn. And it's this sort of cyclical coupled behavior. So that can combine all of our simulations into one piece of software. So that's going to be quite advanced, I'd say. And we're going to be working with Leap Australia, who are our sort of software help, I guess, our software mentors, and we'll be looking at this down the track. Oh yeah, so Leap Australia, they're our engineering software consultants. That's the word I was looking for. And they're going to be providing assistance with not just ANSYS, but also Onshape.
Awesome. So this is what we'll be kind of touching on for our next workshop. We're going to be spending 2 weeks working with OpenRocket, but it's essentially a simulation software that you can kind of use Python alongside with it to customize the. I'm not too sure what that last point means with like drag, thrust, and gravity in 2D.
Sorry, I'll help you there, Ann. So the basic code of OpenRocket only takes into account certain variables when it runs its simulations. The Python code that the simulations team are developing are going to be augmenting the abilities of OpenRocket simulation software to incorporate drag, thrust, and 2D gravity vectors so that we can get more accurate simulation by sort of adding to the already existing capabilities of OpenRocket.
Awesome. Yeah, cool. But basically what we would be doing for the first workshop coming next week will be learning OpenRocket and try and design a rocket that is able to fly. So what we're going to be interested in looking at is the flight stability. So that concept of center of gravity and center of pressure will be the two indicators that we're going to try and design for our next workshop.
Mm-hmm. Oh, and these are just a couple of bigger screenshots that you can see. So yeah, you can select different components and you can select materials to adjust the weight of all those components. You can adjust the shape of the nose cone, like Anne was mentioning, all those different nose cone shapes. And there's all these different components that you can add, and it creates this little model down the bottom. It calculates the center of gravity and center of pressure for you. And you can fiddle with all of these design parameters and then run some simulation, and it will tell you acceleration, altitude, velocity, all of that good stuff. Now, this is the overall workflow of the Phobos project. So this is how we're going to be using all these different softwares together. What we're going to do is we're going to model in OpenRocket first of all, and use the info that Anne was mentioning to see, is this going to be a stable flight? And then we'll start building a 3D model in Onshape. And yeah, these two will sort of go back and forth between each other. And then once we have our 3D model, we will put that model into ANSYS and apply coupled FEA and CFD. This ANSYS Fluent just means the CFD package that's attached to ANSYS, and we'll apply this coupled simulation to check what kind of center of pressure and center of drag we're getting. And then we can go back to OpenRocket and say, well, do we need to adjust something because that didn't quite work? And it's a loop. We go back and forth in this loop. And
awesome.
Wow, we actually got through it. That's amazing.
Thank you guys for like going through 50 slides with us.
Yeah.
But yeah, so for the next half of the semester, we're going to be trying to build our own rocket. So we're going to start with designing a rocket. We're going to be CADing that rocket, and then we're going to be in the end 3D printing it and then trying to launch it, hopefully maybe after exams to launch it. But this is kind of what our structure will look like for the next few weeks. It will be 2 workshops of OpenRocket. So we're going to try and build it on OpenRocket. Then we've got mid-sem, so, kind of study hard about that, and we'll skip a workshop. Then afterwards, it's LaTeX. That's for more of the report writing side. So we're going to try and learn how to use LaTeX for that report writing side of the competition. And then it'll be Onshape, which is CADing, 3D printing it, hopefully, using our MSc access to the workshops. And after we 3D print it, we will hopefully be able to launch it after the semester. So yeah, exciting things. I'm honestly looking forward to building my own rocket.
Yeah, we'll be doing it with you. Like, we're learning with you. We're all in this together. So it's going to be fun. Awesome. Well, thanks everyone for coming. And yeah, we'll see you next week at the same time on the same Zoom link, and we'll be talking about OpenRocket.
Okay, I think Cody just wrote on the chat if these rockets are for L1 licenses. No, from my belief.
Yeah, they're not. The L1's larger rockets. We're going to be doing little model rockets.
Yeah, so these are baby rockets. We'll call them L0s or something.
That's great. Yeah.
But if you're interested in L1s and getting your certificate for L1s, definitely reach out to either us and we'll connect you to Ben, because I think he's kind of like the man that kind of organizes all that stuff, or Harrison. So if you're interested, give us a buzz, and we can kind of contact you or connect you to the right person to talk about L1s.
Yeah, I think they're doing a launch on the 10th of April for L1s.
Yeah,
So yeah, if
yeah,
you want to join in with that, just let us know and we'll
yeah.
hook you up.
We'll organize carpooling and everything to try and get people to get there. So yeah, if you're interested in attending, I don't know if we'll do a thing to figure out who's attending. But yeah, that's going to happen on April 10th.
I'm not sure. Anyway, we'll see you next week.
Awesome. Thanks so much, guys.
Thanks, Anne.